Can you hear the mic? Yeah. Good. So let's get started with kinetics, guys. So far we've been fully focusing on kinematics, 2D, 3D, with all kinds of coordinate systems, Cartesian, what is natural or intrinsic to the any curved path, including 3D, and then of course the polar and cylindrical coordinate systems for 2D and 3D respectively. Now we want to factor in the causation of the motion. So typically, if you're looking at it, what is most intuitive is in any solution process, you are essentially connecting the cause to the effect, and if you're looking at the cause, it's typically the force, and the effect is the displacement that you have. And this is in a generalized sense that a force could be a moment as well, so includes both F and M, whereas this could include both rotation as well as displacement, let's say U, right? So the overall idea is essentially to connect these two, and typically it is kind of, if you try to do it directly, it's kind of a little difficult, so you introduce certain concepts in between to make the connection more effective, so that you can go in a step-by-step process, and that's where all the derivatives of displacement with respect to time start coming into picture. So you have velocity, it's the first derivative, and then the acceleration, and then of course the laws come into picture, of which you're familiar with the Newton's laws as far as F is concerned. Now, which is what we will start as well with for particles and set of particles, but then we will get on to moments where we will be extending Newton's laws. So whereas this goes with Newton, this goes with Euler, which is just an extension to rigid body motion, where we will consider rigid bodies as to be composed of a set of particles which are connected in some way such that the distance between them remains a constant, and then based on that you will be able to get to the solution, right? So these guys lived about a century apart from each other. They had about a decade or two at which they overlapped. The last couple of decades of Newton, Euler was just born, and incidentally both of them had issues with their eyes, and with the right eye both of them had major issues, and they could hardly see with their right eye, and Euler towards his 20s developed that problem, and towards his 50s he actually lost his second eye as well, the left eye, and that became the most productive part of his career actually, very interestingly. Newton of course was British, Sir Isaac Newton, and Leonhard Euler was born Swiss, but he lived almost all his career in Russia, in particular in St. Petersburg, taken care of by the Russian Tsars who kind of protected him, and you would see a lot of that Russian influence in terms of his work, and he has a huge bearing on my advisor, apart from his major scientific and mathematical contributions in many different areas, also because of the way Euler was able to integrate spirituality and science, and that's something which my advisor took pride in as well. He used to conduct at Georgia Tech weekly Bible classes and things like that. So he was really deeply influenced by both the mathematics and physics of Euler as well as his religious leanings. So though we say that the extension is from particles to rigid bodies, it's not that Newton didn't apply his laws to rigid bodies or bodies rather, like planetary bodies. For example, he studied planetary motion. You know, the Newton's laws of universal gravitation as well comes from that. And also interestingly, the inertial frame of reference that I keep harping upon so many times and stressing that you mentioned that, it's also sometimes called the Newtonian frame of reference, and sometimes it's also called the Galilean frame of reference. These are all kind of synonymous with each other, Newton inertial and Galilean. And the reason for that is that actually, if you look at most of Newton's laws, they were already in some form or the other already in Galileo's work, and which is why a lot of credit is given to Galileo also in terms of calling it the frames of reference by his name, but the laws are usually referred to by Newton's name. So the extension is something that not only introduces the concept of moment and therefore the relationship between moment and theta, and in which case we bring in those concepts which we have already introduced, namely your angular velocity and your angular acceleration as well. So this is what kind of establishes that connection. So as far as the relationship at this right end of the spectrum is concerned, that's where we were dealing with kinematics as the description of motion, whereas now the relationship between generalized forces and generalized accelerations is what is essentially your equilibrium equations, which is nothing but what you studied in statics in terms of drawing free body diagrams and trying to balance out forces, balance out moments, etc. Here that just an additional force is coming into picture, what is typically known as the D'Alembert force, which is nothing but the negative of the mass times the acceleration. So if you can deal with the minus m as additional force, pseudo force that is being applied, then all your statics principles hold, because just that you're adding that to the left hand side, the sum of the external forces, and the total forces become zero once again, and you try to solve those equations. Okay, so these are all equivalent ways of saying the same thing, and this extension from particle to rigid body not only involves the introduction of moments and angular motions, but also translation of the rigid body is still there. And the translation of the rigid body is now not in terms of the set of particles that compose, but just the motion of one particular point. Typically the center of mass is taken into account. So all translation is defined in terms of that. So that is again what some part of which Newton had already done when he had studied planetary motion around the sun. So he had taken into account the masses of the planets, the masses of the sun, and the distance between them, and what kind of path they could come in. Even though most of that planetary motion is attributed to another great scientist by the name Kepler, and Kepler's laws come into picture over there, right? So this is the overall setup. So it's very important to remember that the actual things that we are interested in is in the force and the displacement, but we cannot connect them kind of directly between the cause and the effect. Sometimes, of course, this could be the cause and this could be the effect, in the sense that I want to have a certain displacement in this. So what is the force that I have to apply? So that you can think of the problem being posed in an inverse way. So in that sense also you can see, but unless and until we introduce these time rates of change of the displacement, it's not possible to connect the force, and which is how all of this eventually comes together. So this portion is kinematics, and as you know, this is essentially your kinetics, or the study of equilibrium and dynamic equilibrium, as opposed to the static equilibrium that you are already familiar with from your statics class. So this is to start with. We will not get into moments. The initial part of today's class will just focus on translation, which we are by now very familiar with in terms of how to handle for particles and systems of particles as well. Then we will try to combine for the entire system of particles, and then see if in a special case where that system of particles happens to be a rigid body, which of course has infinite number of particles, but based on the fact that the distance between any two chosen particles remains the same throughout the motion, you can actually simplify that instead of an infinite degree of freedom system to a finite degree of freedom system, which is essentially 3 translations and 3 rotations. That's as far as 3D motion is concerned, but we'll also study 2D motion as a special case where we'll be dealing with only 2 translations and 1 rotation. So in that sense, like many of the example cases that you worked out were all 2D kind of motions, kinematics, where you are looking at only 1 rotation, and therefore a relationship as far as the m, alpha, theta, etc. is concerned can many a times be done as a scalar equation instead of a vector equation, because only one quantity is involved. Just like in rectilinear motion, we were looking at just one translation involved, and therefore we didn't need to complicate things with vector equations. Scalar equations were something that we could live with, right? So based on that fact, we will start with the translation, but once we extend that from a system of particles to rigid bodies, we have to introduce the concept of the center of mass. So that's something that you'd be already familiar with, but we're introducing it from the point of view of how we need it in dynamics. And then of course when we generalize this to rotation as well, apart from the center of mass, we'd also be looking at an axis about which we would need certain moments of inertia or products of inertia, etc. So we will visit that when we go to. So you will keep seeing this abbreviation quite often. Rigid body dynamics is what I mean by RBD. So in most of the slides I will have the end result, what I would like to get to eventually, and what it is about, and then we will talk about the steps involved in getting to that. Now though most of the time we've been writing it as mass times the acceleration, this version of the Newton's second law, the actual more appropriate version is this, where you're actually looking at the rate of change of the product of mass into velocity, and this will of course play a very, very important role as we go forward. This is nothing but your translational momentum. In most books it's written as linear momentum, but as I mentioned in a previous class, I avoid that because of the confusion between linear and non-linear. So I distinguish rotational by always calling it translational. So translational momentum is what we are looking at, and that's a vector, as you see, because velocity is a vector, right? So now in getting to that, of course, and also, you know, this is Newton's second law, but Newton's first law can be thought of as a special case of this, where you set the left hand side to 0. So then you say that the rate of change of your velocity is equal to 0. In other words, your velocity is a constant, which means that it maintains the direction and the speed, which could of course also be 0. So special case where v as well as f are 0, but even when just f is equal to 0, you could have v as a constant, because if you assume m also to be a constant, and therefore Newton's first law is a kind of a fallout of a trivial situation as far as the second law is concerned. So this goes back to the publication 1687 of In Principia, which is where the where Newton first kind of produced this particular result, as well as other things based on his observations. And of course there are certain assumptions involved, and as I always keep stressing, it's very important for us to be aware of these assumptions, most of which you are already familiar with, because we want these assumptions to be well understood, so that you know where you're applying it, is if it is really applicable or not, so that you don't end up applying it to problems where it's not really applicable, or if it's not applicable, what are the changes that need to be made in order to make it applicable. So that's something that we can think about. So the first thing is, as I said, synonymously used with inertial is the adjective Newtonian and Galilean to refer to frames of reference which are neither accelerating, which is not accelerating, because within accelerating it all involves both translational acceleration as well as rotational motion, because once rotational motion is there, there is an acceleration, and so therefore frames of reference which are neither rotating nor are they accelerating in a translational sense, those are typically what you call as this. But most often you would have every frame of reference is accelerating or rotating in some way, and the reason why it still works is because those accelerations are much smaller compared to the accelerations that we are interested in, and therefore, for example, you can take the radius of the earth and its period is 24 hours, the radius is about 6,400 kilometers, so then you can see what is the rate at which the acceleration is taking place. Compared to many of the problems that we will be looking at, what are the acceleration magnitudes, that will be very, very small, and therefore within the engineering uncertainties, because all measurements also involve uncertainties. This is another important thing to remember. In your problems, we are giving you specific values of certain input data in terms of angular velocity or distances. You know that none of those can be measured exactly, right? So there is a certain tolerance, plus or minus, depending upon the methods used for the experimental determination of those values, and therefore within those uncertainties, the fact that you're using a non-inertial frame of reference which is having very low accelerations will make it something that is not a big issue indeed. Okay, so but it's good to be aware that when you are dealing with accelerations of that order of magnitude, then you do need to take that into account. For example, the way we keep track of time, so even the seconds that we measure usually using classically using the simple pendulum. So that simple pendulum, its period we think is constant, but it changes over the day from noon to midnight. There's quite a substantial change, and it's only the average period that we are looking at as a second in order to take it as part of the time. So, and why is it changing? It's precisely because of the problem that I just mentioned, where you're looking at the sun, because you're not supposed to look at the sun. So this is the earth that you have, and during the daytime, of course, it's a point somewhere on this hemisphere that is actually facing the sun, and during the night at some point over there. Already you see the distance from this point to this is going to be slightly different from each other, and therefore the rotation, revolution, all these things are going to be affected. Of course, the moon is going to exert its own gravitational force on this, and that is also going to affect, and because of which it's actually observed when you're looking at very precise clocks that these pendulums have to be corrected for over a period of a month at least, so that you take care of the motion of the moon around the earth, which is typically about a month, and then the that kind of almost ensures you reasonably precise value for the second. Okay, so the second thing, of course, is if you want to use the right end of this equation, that is equal to mass into acceleration, obviously you have to ensure that the mass is not changing. So that's something you have to be aware of, and when you're using it for rocket equation, etc., obviously it is this that you have to go for, because the propellant is burning, whether it's solid or liquid, it's getting the exhaust is going out, so the total mass is reducing. When it's a multi-stage vehicle, then you're dropping off the stages after they are done, and therefore the all the hardware which goes with the stage also gets reduced. It's not only a continuous reduction because of the propellant, but also a kind of reduction which is discrete, that is happening because of the stages that are separating out, right? So then so that has to be taken into account, but of course that is valid only for this part. As far as this part is this equal to sign is concerned, that assumption is really not necessary or not made, right? So, and the other important thing is that this is valid only for particles. As I said, it's essentially Newton's legacy for us, and the extension to that by Euler is something we will look at the latter part of today's class, right? So it's valid only for particles and bodies if idealized as particles, which is what Newton did. For the kind of problems that he worked out, those were reasonably accurate assumptions to make, and including for the sun and the planet, such massive objects considered as a single particle, all of their mass concentrated at their centers of mass, and still it works. Okay, then coming to of course, as I said, Newton's first law is a special case of second law, so we can deal with the second law alone, and we will introduce the third law as and when we need to include it, and that is something which is the major contribution of going from Newton to Euler, from the particle to the rigid body. You will see how we are going to actually utilize that Newton's third law in order to make the equation for the rigid body not an infinite degree of freedom system, not an infinite number of equations, but just 6 equations of motion for each rigid body. How can we do that is primarily because of Newton's third law, right? Then so what is important is that the actually in Principia you actually see, instead of an equal sign, it's actually a proportional sign. It's only because we wanted to honor Newton and gave the force a unit called Newton, and we said that 1 Newton is the force which is required to accelerate a 1 kilogram mass by 1 meter per second squared. So we introduced a new system of units and new unit called Newton, Therefore, that became equals, in other words, the constant of proportionality became 1. I could have used any other unit for force, then you should have put in that appropriate constant of proportionality, right? So essentially it's a smart choice of units which has made that proportionality constant equal to 1. As I said, the extension of course is by Leonhard Euler. He extended Newton's second law of motion to rigid bodies, and by rigid body we mean that from the infinitesimally sized teeny weeny particles that we are looking at, which could be represented geometrically by just points, we are now giving it a finite size, from infinitesimal size to finite size, a certain shape, and which is maintained, the size and shape are maintained, which is why we call it rigid, as opposed to elastic bodies which you'll study in structural analysis, or deformable bodies, for example, the courses that you have. And then of course the other important aspect when we get into the dynamics is we will see the distribution of the mass matters. Whereas the point, everything was concentrated at a point, so we are not really interested only the total value of m. Here the total value of m of course is important for the translation of the center of mass, but in addition when you want the moments and the angular motion, you do need to have the actual distribution of the mass, because that's going to affect the mass moments of inertia, for example, and that can quite drastically affect the equations relating the moment to the angular acceleration alpha. Any questions or doubts on this? Fairly straightforward, right? So Leonhard Euler, you can see his right eye. So this is an actual painting that was kind of done in his 50s. There's also another painting which is available in original in some of the Swiss museums, where you will see in his 20s, you would see both his eyes pretty much quite healthy, and his contributions of course you see in lots of areas. The laws of motion, which is what our course will be focusing on, of course. Then of course a little more advanced courses on engineering dynamics will introduce the concept of what are known as Euler's angles. As I have been repeatedly telling you, the displacement is a vector, the angular velocity is a vector, and the angular acceleration is a vector, but theta is a very, very difficult quantity to deal with. Many of the vector operations will not work for it, except when you're dealing with infinitesimal rotations. When you're dealing with infinitesimal rotations, you can have an infinitesimal rotation vector. But once you have finite rotations, you will have to use certain specific special types of representation of the rotation. One is called Rodriguez parameter, used quite often in deformable bodies or structural analysis. But the one which is more commonly used in other situations is the Euler's angles, and Euler's angles of rotation play a huge role over there, right? So that's Euler's angles that you see there. Then of course when you go to minimization problems, which you will see, for example, when you're dealing with work energy kind of methodology, we were going to integrate the Newton's law, Newton's second law, with respect to the displacement. We're going to get work done by external forces on the one side, including of course moments. Whenever I say forces, most of the time I mean it in a generalized sense. And the other side, of course, when you're integrating mass into acceleration with respect to the distance, you end up with a certain quantity which is essentially going to give you the energies and the changes in energy if it's not a conservative system. And most of those problems you will be dealing with what are known as functionals instead of functions, which you know is like a y equal to y of x is a function, but you're going into dealing with functions of functions, what we call as functionals. And then you extend calculus to what is known as calculus of variations, and the most important fundamental equation there is the Euler-Lagrange equation, which helps us to minimize such functionals, and therefore out of a set of solutions which are acceptable from the boundary condition point of view, etc., you can find out the specific path that the particle or the body will actually take. And that is essentially what is solved using a set of governing differential equations, which we call as the Euler-Lagrange equations. In fact, the way Euler developed it is not only the differential equations that you would get, but also the associated boundary conditions to get the entire boundary value problem very well defined, so that you can solve that directly. So his work was not limited to rigid bodies and elastic bodies, but also to fluid mechanics, where the Euler equations are quite popular. It's the simplest form of looking at a fluid model before going into Navier-Stokes, etc., introducing the viscous forces, etc. So then the as far as structural mechanics is concerned, once again you have the Euler-Bernoulli beam theory, where Euler and Bernoulli contributed to that. That's the simplest theory that you can have for very long slender structures like these, or the beams and columns that you have. So that's again something you will look at in structural analysis. Then where elastic instability is involved, when you're trying to compress something, just like these columns which are taking the load of the roof over here, beyond a certain load they are going to tend to buckle. In other words, there's an instability. So the critical load there is called Euler's critical load. So again, he has made a huge contribution there. And many of these simple mathematical principles that are developed by him here, which we will be looking at, will actually be the basis of some of these higher order developments, if you would allow me to call that. Okay. So then it's also in terms of numerical solution processes, a lot of things that are used for computational schemes and algorithms today, including the Euler method for solving the ordinary differential equations numerically. So you use it there, and many other things that he has contributed to. So let's get back to what we are looking at in terms of the kinetics. We are going to extend from a particle to a set of particles, because that's kind of an intermediate before we get on to the rigid body, which is a special case of a set of particles, right? So Newton's second law of motion, for a single particle, if you take in that set, there are n particles totally. Then if you number them as 1 through all the way through n, I takes on the values from 1, 2, 3 and so on to n. So we will talk about a generic particle, which is called as the ith particle, that system of n particles. Now if you're looking at the applying Newton's second law to that, obviously force is equal to mass into acceleration, assuming the mass does not change, of course. So that assumption is inbuilt, unless and until I specifically say we will make that assumption throughout the course. So we will assume the mass is constant, so only the velocity varies, and the time rate of change of velocity in an inertial frame of reference is ai, and obviously because it's the ith particle, and this equation of course is valid only when that acceleration is in an inertial frame of reference. Now as far as the left hand side is concerned, it's the sum of all the forces that are acting on that particular particle, the ith particle. What are they? They are things which are coming from external sources. So your Fi that you have, C over here, is the force which is coming because of external loads that are coming because of it could be even, let's say, a gravitational field of another body, it could be a magnetic field of another body, electromagnetic field of another body, etc., or an actual mechanical force, or a distributed force, or a pressure that is applied, or a shear that is applied, whatever it is. But essentially that's what it is. It could be friction, it could be tension, whatever it is. But there is also, because it's a set of particles that we are now dealing with, not an isolated particle in vacuum, we are dealing with other particles which can exert some forces on this, and those are known as the interaction forces. So these interaction forces, the convention that is used in your book, and which is what I follow, but sometimes it is kind of reversed, so be careful about what a particular literature is doing. Here you would see that this is the if small f, lowercase f, that is used over here. This small f ij refers to, on the ith particle, what is the force exerted by the jth particle. And of course there are n such particles, so you have to sum over all of them. Of course Fi bar will be equal to 0, so that's anyway, even though it's included in the sum, that would not make a difference, right? So your Fij is a force, and both of these of course are vectorial, and you have to have a vectorial algebraic addition that is essential, and all the laws of vector addition that we already talked about will of course hold there. So it looks kind of a little more complicated when you are talking of just one particle at a time, but when we go into all of the particles together as a set, you will see a simplification arises, and which is what we will do in the next step. So how to deal with the second term on the left hand side. Now if you sum up all the equations for all the particles, what will happen with the second term here is already it has a summation over j, okay, it has this summation is summation over j equal to 1 to n, but what I am doing in this line is summing over I equal to 1 to n. So just for the second term alone, it will be a double summation first over j equal to 1 to n, and then a summation over I equal to 1 to n. Now when you are having that double summation, these Fij's, you will have an Fij coming somewhere and an Fji also coming up somewhere, and both are getting added up. And now you know that by Newton's third law, these two are equal and opposite to each other. In other words, Fij is equal to minus Fji, and therefore they will cancel each other out, and therefore the second term on the left hand side completely drops off. All that you have is the sum of the external forces acting on the ith particle is equal to the sum of over all the particles. So sum over all the particles, and therefore it's the external forces on the system of particles is equal to the summation of the masses and acceleration products of each one of those particles. Still, we have simplified the left hand side, but there is something that we can do on the right hand side to make it even more simpler than what it looks, because it will involve n terms over here that you have to sum up the acceleration. You have to find the acceleration of each point, and then you have to multiply by its own respective mass and then add it up. The right hand side still seems a little more work to do, but again we could simplify that as well. But first of all, just an explanation what I already mentioned to you in terms of how the left hand side got simplified is that your interaction forces, that is your small Fij, the lowercase Fij, are equal and opposite. So in other words, Fij and Fji are negative of each other, which is essentially an invocation of the Newton's third law of motion, and thus this whole thing will not contribute to the overall system dynamics as such. It is still there. It's not that these interaction forces are not there, but they're kind of internally balancing out. When you're dealing with what's happening to a specific particle within the system, you do have to consider that, but all that you are interested in is the overall system dynamics, then you no longer need to bother about them. Any questions on this? Okay. So next, as I said, we've done some simplification of the left hand side, so let's turn our attention to the right hand side now. Okay, so here's where we introduce the concept of the so-called center of mass for a particle set, of course, not yet to the stage of a rigid body, which is what we eventually would like to work towards. CM, of course, is a abbreviation that I'll continue to use throughout the rest of the course, center of mass. And particles' acceleration is related, of course, to their position vectors. You're all very familiar with that. That's what we have been doing in the first half of this course, where we've been trying to relate the velocities and accelerations to the displacement. So you know that the first time derivative is the velocity and the second time derivative is the acceleration. But since all of these involve derivatives of a vector, either the displacement or the velocity, it essentially means that you have to mention with respect to which frame you take that derivative, right? So unless and until we mention, or that frame would be the inertial frame of reference. So for all these derivatives, there should be a pre-superscript of I that is there, because that's the only frame that we are interested in right now. So that's not explicitly shown, but that's essentially with respect to which we are taking this time derivative. And it doesn't matter which inertial frame. There might be multiple inertial frames that you could have as a choice. Any one of them you could choose, and this should still be valid, because this particular equation is valid for any given inertial frame of reference with respect to which, of course, your position vector should be then from a point which is fixed on that frame of reference, which will anyway be fixed in any other inertial frame of reference also, and they will differ from each other by a constant position vector, which is a measure of how far these frames of reference are from each other, and therefore time derivatives of that will anyway go to 0. So that's the reason why this works, right? So your summation of mi ai, which was the, remember, the problem term that we were still left with over here. So this is the term that we were trying to handle, the right hand side, so which is what we are trying to simplify over here. So What can we do with it? First of all, we can invoke whatever we have studied already in terms of replacing that acceleration in terms of the displacement as a second derivative with respect to time in a particular inertial frame of reference. And then of course you can have it more generically. This is actually an approximation when this equals is valid only when you are having your mass is a constant when you are trying to equate the right hand side to the left hand side, but the actual thing is the product of MI/RI is what you have to take the derivative of, and therefore you are essentially saying d squared by dt squared of a summation of mass times the position vector that you are interested in. Now this is a very interesting term that you have where you are multiplying the mass times the distance from a particular point in the inertial frame of reference, which is fixed in an inertial frame of reference, and then of course its direction as well to account for the position vector, and how that is changing with respect to time is what we are interested in. Okay, still nothing seems to have changed much. In fact, looks like it's even more complicated than what we started off with, right? So let's see what else can we do. Assuming constant particle masses, of course, which is why the left hand side holds, the right hand side always holds, right? Now defining the center of mass location, now we are still not in a rigid body. This is for a system of particles, a set of particles, and the position vector has always be from one point to another point, and we will continue to use these two notations throughout the rest of the course, where we will always call a point fixed in the inertial frame of reference as O, and a point which is the center of mass of either a system of particles or even a rigid body, we will call it by the name C. There are multiple rigid bodies involved, we will give subscripts to C, but essentially ROC is always a position vector from an inertial point fixed in an inertial frame of reference O to the point which is the center of mass of, in this case we are considering just one set of particles and the center of mass of that. Now that center of mass location can be defined as the whatever you see in the within the brackets over here, that term divided by m, right? So it's essentially a weighted average of the position vectors. An average of the position vectors would have been just something, but now we are weighting that by multiplying each term by your mi, and then you are dividing by the total mass, which is the sum of mi, of course, right? So the system mass, because it's a set of discrete particles, the total mass of the system happens to be the total, the sum of the masses of the individual particles, which is your summation of mi. So this is essentially what we have. Now we have a way of kind of simplifying this particular equation, because now your MROC, we can take this denominator to the left hand side over here. So M times ROC becomes that summation of MI/RI, and then you can essentially put this particular thing, summation that you have over here. Instead you can replace it as just M times ROC, which is the position vector from the point in the inertial frame to the center of mass of the system of particles. So once we substitute that there, we get on to a way of deriving what is known as Euler's first equation of motion. We aren't yet there. This is the result that we would like to get by the time we finish this slide, the steps in this slide. So this is what we want to eventually get. What does it essentially say? Sum of all the external forces acting on the system of particles is essentially equal to the mass of the whole system multiplied by the acceleration of just their center of mass. Now I'm not even bothered about on the right hand side about individual particles. All that I'm bothered about is the overall center of mass of the system. How is it moving, and how fast, and therefore how is the speed itself changing, and how is its direction changing, which is all information which is built into the acceleration, as you already know. So how do we get there from what we had at the end of the last slide? So now we have this term d squared by dt squared summation of mi/ri, which we already showed in the previous slide, that summation to be nothing but the product of the total mass times the position vector from an inertial point to the center of mass. So we can just substitute that there, and again For most of our problems, m will be a constant, so it can be taken out of that differentiation. So all that you have is a d squared by dt squared, and the derivative, of course, is the second derivative is in the inertial frame of reference, and that's of a position vector, and therefore once again we invoke our displacement acceleration relationship, and therefore that is your MAC, right? Now we bring in the center of mass definition. Of course, it's quite clear that it's the sum of the particles, each particle's mass into acceleration. Then you take the sum over all of the particles, and then that of course should be equal to the total mass times the acceleration of the center of mass itself, right? Now the same is true for what is known as translational momentum, and this is again an abbreviation we'll use throughout the course because this is a quantity that we will be using very often in the rest of the course. This is TM, stands for translational momentum. Okay, so whatever we have said for center of mass, the same thing holds for translational momentum, because translational momentum is nothing but mass into velocity, and if mass is a constant and can come out, essentially the same thing can be done with mass into velocity. So what we are saying is that just like the statement we made for center of mass, we can now say that the sum of all the particles translational momentum, the plural that is used is not momentums but momenta. So so when I say TMs, actually it means translational momenta, right? So the TM or translational momentum based on the total mass and of course the center of mass of the system of particles, how fast it is moving and in what direction, that is what is essentially going to determine the right hand side. So it's much more difficult to determine the left hand side, much more easier to determine the right hand side, which is why we can now restate Newton's second law as applied to a system of n particles as a summation of all the external forces which are acting on that ith particle. Then you sum over all the particles, and then you end up with the total system mass times the acceleration of the center of mass. So we are no longer bothered about what is happening to the forces of on an individual particle, because the forces on an individual particle, remember, not only involve this but also the interaction forces, the small Fij's. Now we don't have that at all. So there was one simplification that we did on the left hand side. There's also a simplification we did on the right hand side, where we replaced a summation by just a product of the total mass times the acceleration of just one point. Now that point happens to be the center of mass of the entire system of particles. Any questions so far? Okay. So this is what we call as Euler's first law for a particle set's translation. Okay, so just like we would have a law for translation, we will have a law for rotation. That would become Euler's second law for the particle set's rotation, and then these two laws are still for a discrete set of particles. We will then specialize it for the case where we are dealing with a rigid body, where the distances between any two particles, any pair of particles that you take from that set of n particles, that distance remains the same. So we will utilize that to further simplify, and we will see what happens over there, right? So next, so the purpose of this slide is to get to this equation, that summation of Fi equal to MAC, right? So what is the difference? It's the same thing what we had already, right? But what we are going to do now is some kind of an extension that we are going to do of that to rigid bodies. So if you look at that, the equation is one and the same, whether it is for a system of particles or whether it is for a rigid body, it's one and the same. But then in the rigid body, there are infinite number of particles, so we cannot go about making an infinite sum, practically speaking. So these summations will soon be replaced by integrations. But right now we will see in terms of the overall validity of this equation, if it is valid for any arbitrary set of particles, why should it not be valid for a set of particles which constitute a rigid body, is what we are going to see on this particular slide, right? So extending MROC equal to summation MIRI and Euler's first law of motion, which we had at the end of last slide. So again, the equation is repeated here, now to rigid bodies. Now we are going to replace the summations on the right hand side with respect with integrations, and when we want integrations, instead of M's or MI's, you're going to have dM's, which is that infinitesimal elements mass, and then we have to integrate that. Now when we want to integrate dm, it's not possible to do it as it is, so we'll introduce the concept of mass density rho, and then we will call dm as rho dv, right? So the mass density times the infinitesimal volume element, and then we will be able to go ahead and do the integrations, and many times we will have the position vector or acceleration or velocity involved in the right hand side. Those are also involved in length kind of parameters, so they blend well with an integration with respect to the volume element, which involves anyway dx, dy, dz in a Cartesian coordinate frame, or for that matter any other frame of reference, r d theta, r dr d theta dz in a cylindrical coordinate system, or you would have r squared d theta d phi dr in a spherical kind of system. Whatever it is, essentially the volume element is much easier to deal with when the other quantities that you are having are essentially all these are based on your position vector, which is also involving certain length quantities, right? So your center of mass location now, therefore, we earlier remember had summations. All those summations are replaced by integrations. All those MIs are replaced by your dMs. So it just becomes an integral of r times dm, where r is the position of that particular infinitesimal mass dm from, of course, O, which is a point fixed in your inertial frame of reference, which is why, of course, the left hand side is r subscript OC. Okay. So now the denominator, of course, remains the sum of the system of particles mass, which of course in this case becomes the mass of the rigid body, which is your integral of dm, right? Now we, as I said, we introduce the concept of the mass density. I say mass density because there are so many other kinds of densities that you will encounter going forward. So it's important to know that this is a mass per unit volume, so a density associated with masses. Okay. So then you have the right hand side as rho dv, and therefore your ROC can now be written as, all that you're doing is you're keeping R as it is, you're just replacing this dm as rho dv, and when you do that you end up with rho r dv in the numerator, and you have an m in the denominator. Okay, and of course once again your mass equation also can take advantage of the density concept to find the total mass. So thus your Newton's law, which is applied now to a rigid body instead of just a particle or just a system of particles, is now applied to a special kind of system of particles, which is the rigid body, and the sum of all the external forces which are acting on the rigid body should be equal to an integration of an acceleration times dm, and that acceleration of course is of each of those individual infinitesimal mass elements dm, which is why we're not putting any subscripts to that to say which particle, because it's all the particles which compose that particular rigid body, but since we have replaced that summation with an integration, we're not dealing with those discrete set of particles but in a continuous sense, and therefore we are having that integration. So A becomes a continuous function of all the points that constitute that particular rigid body. So it could be a function of x, y, z, for example, or r theta z, or it could be a function of r phi z, or it could be a function of your intrinsic coordinates as well, depending upon which you prefer to use for a particular problem, right? So your summation fi, so left hand side remains the same. At the right hand side you are replacing once again your dm as rho dv, so that your Newton's law now becomes an integration of the mass density times the acceleration times dv, the infinitesimal volume element that you have here. And this is what we call as Euler's first law of motion for the translation of rigid bodies. Now what we had on the previous slide was a set of particles, any arbitrary set of particles. Now instead we have RBs or rigid bodies, and this is of course the equation wise it is exactly the same as what we had there, just that the way your some of these quantities are defined is going to be different. There we had just summations, here we have integrations. That's the only difference. Any questions or doubts on this? Okay, we'll move on. So now how do we deal with actual practical problems, because soon you're going to get another homework set. So not today, but maybe after Wednesday's class, I'll give a homework set which will be due the Wednesday after that, right? So that's next Wednesday. So this is rigid bodies. Many a times might be just simple sphere or cuboid, let's say a prism or things like that. Very straightforward, direct, easy to deal with. But when you're dealing with something which is a little more complicated, many a times you can still see that maybe you can think of it as composed of certain standard shapes which are just kind of put together. You would have seen that in many of your examples also already, but just that we didn't need kinetics or mass or inertia related quantities over there, therefore we didn't bother about it. But if you look at it, go back and look at some of your homework problems, many of those systems were like either circles or cylinders, or you had bars or plates or moving plates, whether they're moving or not, the shape and the size were certain standard shapes. So many of your textbooks, your textbook or many of the other books on engineering dynamics will typically list in an appendix a set of tables in which they will list out the properties like how to calculate the mass, and later on we will see another quantity of interest, inertia, that you will need for many of these problems. And therefore if you know them for certain standard shapes, you don't need to keep re-deriving them every time. It's good to do that for a few cases just to know how it is done, but then in many cases you may not have to do it from first principles, from the scratch. You could just sum up the quantities in an appropriate way in order to see how, for the complicated shape that you have, how you can deal with it. So this is for multiple parts. So as I said, standard rigid body shapes, most books like your textbook will list the location of the center of mass. So you don't need to calculate every time summation Ri mi divided by summation mi, or the integration version of that with rho dv involved instead of dm. So that is something that you don't need to most of the time do. You could take advantage of those tabulated values for the center of mass locations from any given arbitrary point. If you are interested from some other point, you can take that and then add it to the new point that you are interested in. What is its position vector from the position vector point from which for which these are given, right? So then there are also certain shapes which are which may not be given in the book, but you could probably take advantage of as soon as you identify there is an axis symmetry involved or certain planes of symmetry which are involved. In both of these cases, you will know that the actual center of mass will lie on the axis or plane of symmetry. An aircraft, for example, fairly complicated shape, right? But if you look at the empty aircraft, for example, you could see that the longitudinal plane which passes through the nose to the tip of the tail is essentially a plane of symmetry. So in other words, what you call as the xz coordinate, y being along the span of the wing, so that xz is a plane of symmetry. So almost always you will have the let's say the center of mass occurring on that. But there are exceptions. For example, if you have a fighter aircraft where you have launched a rocket from one of the which is an ammunition on, let's say, the starboard wing, you still have that equivalent ammunition on the port wing, and therefore you would have a mass imbalance, and therefore you could slightly move towards that which is not yet been utilized. So that towards that ammunition side. In this case, the example that I discussed, the port side. So, but otherwise, most cases you will see that rigid bodies will have many of the rigid bodies that we will deal with will have either an axis symmetry or a plane of symmetry, and in that case you know that the center of mass will be either on that axis of symmetry, which is a body formed by revolution, or on the plane of symmetry as in the aircraft example that I just gave you. And as I told you already, many such rigid bodies will be a combination of such standard shapes, and therefore you can take advantage of that. So how do you take advantage of that? You would treat each one of those sub shapes as essentially concentrated at its own center of mass, and then treat it as a particle, and therefore now you deal with a system of particles, as many particles as you had the number of parts in your rigid body, so you would be essentially dealing with that, right? So you use therefore the particle formula, to calculate the rigid body's, overall rigid body's center of mass, using of course each one of those subcomponents, parts, mass, mi, and their centers of mass is what is their position vector, namely Ri. So it will be your summation mi Ri divided by summation mi, and that will give you your position vector for the overall center of mass of the entire rigid body composed of those subsystems. So yeah, so that's why we remember included the rho dV in that. So that rho, you have to take care of the fact that rho is varying in different parts. So of course if it's varying within that subpart itself, then you have to redo the derivation. So you can't just blindly take that. But it could be that some subparts, a cylindrical part is made out of aluminium, let's say a cuboid part is made out of steel, then you take the appropriate densities when you do the averaging out, which is why of course the weightage is there in terms of the mass, which will of course involve the density as well, right? So this would become of course for that subpart the density of the material that it is made out of times the volume of that material, and if each subpart is made out of multiple materials, then you will have the summation of rho I Vi for within that subpart itself. Okay, so these are of course equations that we already saw for the set of particles, discrete particles. We are just repeating that with different meanings now. Now mi are not masses of individual particles, but masses of individual parts which are also rigid bodies, but sub-rigid bodies of another bigger rigid body that you are dealing with. And similarly the Ri's of course now are the position vectors of the centers of mass of each one of those sub-rigid bodies. And of course the total mass is the sum of the masses of all the rigid bodies. Now the goal of this particular slide is to get to Euler's law again, Euler's first law, but which we already know of course, but now we want to get it in terms of a new quantity called the translational momentum. So we want to get that in terms of translational momentum, and this is a symbol that we will use in the lectures for the translational momentum, a vector L. The translational momentum of a particular rigid body is L, then the time rate of change of that translational momentum is of course equal to the sum of the external forces acting on that rigid body, right? So the translational momentum of course is a vector because it's mass times velocity, velocity itself being a vector even though mass is a scalar quantity. Now for individual particles we already know what is translational momentum. It is mi Vi. We just want to specialize that for a system of particles to start with, and then of course for the special type of system of particles which is your rigid body, right? So for particle sets, your translational momentum L is given by summation of the individual Li's, which is mi Vi as in the first line. So once we do that, we can substitute of course going back to our kinematic equations where we had the velocity in terms of the displacement as a time derivative in an inertial frame of reference. So that's something that we incorporate over there, and of course this is when these parts are valid only when you have the mass which is not changing, whereas for a more general situation where mass is changing, which you will find even in the, not only in rocket engines, even in an aircraft, you know that you are having the fuel burning out, and the aircraft which is landing is much lighter compared to the aircraft which took off. So you have to account for that change as well if you want accurate descriptions of motion, right? So many a times it's important to put your M inside, especially in vehicles which involve fuel consumption. It's more important in the case of a rocket because even the oxygen is carried by in the form of an oxidizer by the rocket engine, whereas an aircraft is using only fuel burn. Air is being used from outside as the oxidizer. So which is why the rate of change may not be that high as in many rocket engines. And also of course rocket engines, as I said, after a stage is used up, the separation of the stage will happen and that will drop off. So discrete changes there apart from the continuous changes. So now this as far as the set of particles is concerned. Now we bring in the rigid body. So it's in terms of just its mass and ROC, or even for the set of particles, discrete set of particles, you can always find its center of mass as we already discussed, and we can put it in this way, and therefore it just becomes mass times the velocity of the center of mass. So this is a very, very important result. So even when you have a discrete set of particles, you don't need to calculate your translational momentum by calculating the translational momenta of individual particles and then adding it up. You can just get the velocity of the center of mass and multiply it by the total mass of the system of particles. You'll get the same answer anyways in a much simpler way. Okay. And for rigid bodies, of course, it's again MVC, but that M is distributed as infinitesimal masses dm, and therefore there has to be an integration over dm and the velocities of each one of those infinitesimal masses dm, which we call as v over here, and therefore we can replace dm as once again rho dv like we did in the previous slide. So we get the translational momentum as an integral of rho v dv, right? So therefore this is a direct fallout, is a most simpler form of the Euler's first law that we have seen so far in terms of translational momentum, that is just the time rate of change of the translational momentum is equal to the sum of the external forces that you have. So now we are done with translation as far as this class is concerned. We will now look at the other part of the motion of the rigid body in dynamics, which is rotation, and this will obviously involve the concept of angular motion. Now, as you know, we already finished chapter 3. Whatever we are doing in today's class is in McGill and King. It's the section is chapter 2, and right now we are foraying into section 2.6, which talks about rigid body rotations in using the concept of angular momentum, very similar to the translational momentum that we already introduced. So just like we said that translational momentum is a vector, beware. Here also the angular momentum is also a vector, just be aware of that, right? And it's very simply defined once you have defined translational momentum as the moment of the translational momentum. So what do we mean by moment of something? It's just you're crossing with the position vector r with respect to some point about which you're taking the moment. So in other words, for angular momentum, it's important to also specify with respect to which point you're taking the angular momentum, because the value of the angular momentum and how it changes will drastically alter based on which point you're taking the angular momentum about. And this is somewhat similar to when you take the time derivative of any arbitrary vector, you should specify the frame of reference with respect to which the time derivative is taken. Very similar to that here, in addition to time derivatives, you are involving a moment, and that moment has to be about a point. So the specification of that point location is very important, and it is possible that point is also moving as the motion takes place of the overall system, and therefore you have to account for the motion of that point as well. It could even be accelerating for all you know, right? So it depends on the point about which the moment is taken. So it's a very, very important thing that many people lose sight of. They think just like translational momentum, etc., which is just a quality of that particular system at a particular instant in time, whereas here it is also dependent on a system at a particular instant in time, but it also depends on the point about which you are taking the moment, and therefore angular momentum needs a very explicit specification of that, right? So for a particle, of course, the angular momentum is about another point p, and that is your angular momentum about let's say a point pi that you are interested in, and therefore it is the position vector of that point pi crossed with mivi, which is your translational momentum. So the moment of that momentum is what you are interested in. So, and the notation we will use, just like we introduced the quantity L for the translational momentum, we will introduce the quantity H. Once again, it's of remember a body, it could be for example, but about a particular point. Here we are talking of for a particle. Now if we want to extend from a particle to a set of particles, obviously you have to sum over HPI. HPI is for individual particle, the ith particle. Now we have to sum over all the n particles, I equal to 1 to n, and what you will be summing, of course, is the right hand side of the equation that we already introduced. So this is what we mean by moment of something is an r cross that quantity becomes the moment of this particular quantity on the right hand side of the cross product. So now the angular momentum about any point P which is related to the angular momentum about the center of mass C and the moment of the translational momentum about that point P. So in other words, when you change the point, you don't need to keep recalculating the angular momentum from first principles. You can just use this equation. If you have already calculated the angular momenta about let's say the center of mass of that set of particles, then you already have hc. Then to get a h about any other point P, all that you have to do is to take the position vector from P to C, and then you essentially cross that with your translational momentum, and then you end up with this. So obviously you can get that from the very basic definition of your L and H in terms of the system of particles. You can just either substitute in this and see, or you can start with one of them on the left hand side and expand it out in terms of its first principle definitions, and you will very easily see that this is indeed the case. Now this is an equation that is very useful because once you have done this, you can get it about any other point, just because all the things that you need, and it's very similar, remember, to how you're calculating the velocity of 2 points based on velocity of one point whose velocity you know to the velocity of another point whose motion you don't know. You are using omega cross that thing, right? So position vector. So similarly you could use this, and that of course was valid for any arbitrary vector also. If you want the derivative of a vector with respect to one frame, you could get it with respect to some other frame by taking the angular velocity of one frame with respect to the other into account. So these are all essentially very, very analogous kind of equations that are falling out from those kinds of, yeah.
Why is it P to C not C to P?
This one, right? Yeah.
If you're going about a point and you want and you know the center of
Right.
yeah.
No, because you're taking the moment about that point, so that becomes your about which you're taking the moment. So this is very different from, yeah, in that sense it is different from the other analogies that I gave you. So this is going from that point P to C because you're taking the moment about that, so that becomes kind of the reference for you from which everything else is measured, right?
So
yeah.
Basically it's fine. If you're doing it about point C, then you use
No, you already can determine HC using this. So if you know the position vector of C, so because you have found the center of mass by using summation mi ri divided by summation mi, or in integral versions of that. So once you have done that, you have the position vector of that, right? So based on that, you can get HC quite easily, that you can hold as a standard, and then you can get H for about any arbitrary point using this particular equation, right? Now this is valid for any arbitrary point, but you don't need to keep getting for each point again and again. Yeah, exactly. You use this equation for taking P as C, and then for any other P, you can use this equation to calculate in terms of it. Okay, now we get on to a little more complication from moving from Euler's first law to Euler's second law, which involves the moment and how it is related to the angular momentum. Once you see the end result, you'll see after all it's not all that complicated, because there's once again an analogy with the first law, just that things get replaced. Instead of translational momenta, you will have now angular momenta to deal with. Instead of L's, you would have the H's to deal with, and instead of the forces, you'd have the moments to deal with. Okay. So once again we start from the basics, Newton's second law for the ith particle in an n particle system. Once again we introduce the complicated stuff on the left hand side in terms of involving the interaction forces between the particles, Fij, small Fij. Now, all that we are going to do differently from the previous derivation is that we are going to take from the very first equation moments and moments of each term. So we will have a pre-cross multiplication by the position vector of that particular point pi that you're interested in, about which you're taking the moment. So your RPI from some inertial frame point, fixed point in an inertial frame, which we typically will denote by O, right? So then you have this. So next we of course sum up. There we summed up before taking the cross product. Now we are taking a cross product and then doing the summation. So once again you would see a double summation of your Fij's will go to 0 because of the same reason, Newton's third law, and therefore the left hand side you will be left with only one term instead of two. That is essentially your first term, of course summed up over all the particles I equal to 1 to n. The right hand side of course remains the same, RPI cross IAI, which is essentially your D'Alembert's force, negative of D'Alembert's force. You are taking the moment about that, and about the same point of course on both the left and the right hand side. So left hand side has been simplified from two terms to one term, just like we did in the case of the Euler's first law. We can simplify the right hand side as well, which is what we will next attempt to do. So your left hand side of course you can very easily see is the cross product of a force with respect to position vectors is essentially moment about that point, right, which is represented by pi. So you essentially have the moment of all of your forces with respect to p, because a summation is involved. That's what your left hand side is, and that has to be equal to the same equations right hand side, which we are yet to simplify. So right hand side is of course related, just like in the previous example we saw that the left hand side we could simplify by cancelling out the interaction forces. The right hand side we could relate to the translational momentum. Obviously in this case analogously we are going to relate the right hand side to the angular momentum, but is it related to angular momentum? Is it so straightforward as what we did there? Remember the end result what we got there, that the sum of the external forces are equal to the time rate of change of the translational momentum. Here analogously we should get angular momentum is equal to the applied external moments should be equal to the time rate of change of angular momentum. Is it always going to be true? No, it will be true. We will find out only for a specific type of point P. In fact, two examples we will see, and in general it will not hold that the time rate of change of angular momentum is equal to moment, because the choice of P also matters, and there will be a complication in terms of reducing your right hand side. But for two special cases it will work out to be reasonably good. Can you guess what those choices of P could be in order to make your right hand side time rate of change of angular momentum? Remember, same equation we had earlier, summation of Fp is equal to dl by dt. Can I get dh by dt on the right hand side always for all P? No. Answer is no, but it is possible for certain specific types of choices of P. So any guesses on what that point could be? Yeah, that's the only special point that we introduced, so that could be one choice. Anything else? So if you choose P as the center of mass, he is saying that then yes, summation MP will be equal to dH by dt, and where H will be Hc, which is moment about C, center of mass. So can it be true for some other P star, let me call it, so that I can write my right hand side as d by dt of H star, HP star.
It's along the line of action of the force.
Yeah.
It's parallel to the force.
Yeah. So in which case it will become trivial because your moment will be equal to 0, right? Yeah. So a non-trivial. In fact, that will be even more useful. What you said is useful for a lot of applications, but something that will be much more useful because it has many more choices. It's a set of choices. Giving a hint.
Along the axis of symmetry, or is it like a point where dr by dt is 0?
Yeah. So can you think what is such a point eventually?
Boundary point? Is it boundary points?
Boundary points? No. There's not much of a distinction between the points on the boundary and the interior here.
Axis of rotation?
Yeah, that's what he said, but yeah, that's also. And there's a reason why that is true, because the more general answer will take that as a subset.
Maybe subset.
Both of these answers are subsets of the real answer.
No, the center of mass is not, so that's a special case, so you get full points for that. But these two guys have to generalize to what they said already.
Instantaneous axis of center.
Because otherwise it will anyway not be, so that is true. So. In fact, it's so general, it's so very useful that, which is why otherwise we'd perhaps not even be studying the concept of angular momenta, because if that were not true, the applications will be so limited for the concept of angular momentum. The fact that I can use external moments is equal to rate of change of angular momentum is what makes this so useful, and that is valid not only for center of mass but also for any point which is fixed in an inertial frame of reference. For any point which is fixed in an inertial frame of reference, it is still valid, and which is why the instantaneous axis of rotation or the axis of rotation is also a case where, because that is a line which is common to the inertial frame and the body. Yeah. So Euler's second law now in terms of the angular momentum of a point which is fixed in an inertial frame of reference. So I'll have to live by my words, so I have to show what we said is indeed true, right? So now you take the moment about any point, which is arbitrary point, we'll call it as O, but the only condition is that it is fixed in an inertial frame of reference, any inertial frame of reference for that matter. Then the angular momentum will now be HO equal to Ri cross Mi Vi, because that's the position vector of that particular point. So the O that you are talking about, right? From O. Right? So the angular momentum's rate of change now, if you take, that is essentially you're taking the time derivative of the first equation in an inertial frame of reference, because it's important to specify that the pre-superscript I over there, that because it's a vector whose derivative you're taking. So it's the summation of, obviously, you have to look at all the quantities which change with respect to time. In this case, once again, we are assuming that Mi is not changing with time, otherwise you'll have one more term associated with that. Otherwise, you know, only Ri and Vi are changing. So once you take the derivative with respect to Ri, keep Vi as it is. The other time you take the derivative of Vi, keep Ri as it is. Once again, all these derivatives being that of vectors are with respect to that of an inertial frame of reference. The summation remains for the system of particles. Now we take it further and then simplify the right hand side. Now you see that you have a term which is dr by dt, which you know in an inertial frame of reference is nothing but the velocity, right? So you replace that by Vi. Now you have a Vi cross Vi, and obviously cross product of the same vector with itself is 0 because they are parallel to each other, and therefore the first term drops out. All that you are left with is the second term over here, Ri cross MIAI. Okay, so this is what we had on the previous slide, and now we see that this is what we have right now. Okay, we are yet to prove that this is equal to the moment. Okay, let's do that. So thus, if and only if the point O is fixed in an inertial frame of reference, we'll come to your point, of course, that's another exception, center of mass. So Euler's second law is now therefore your m naught is equal to dh naught by dt. Why? Because from your Newton's second law, mi ai is nothing but the force. Now r cross the force is nothing but the moment about that point which I've chosen, which is the point fixed in inertial frame of reference, point O, which is an arbitrary point on that frame. So that's the reason why this ends up to be you're just interchanging this left hand side and right hand side in this from the yellow equation to the orange equation. So your summation of MO is equal to dH naught by dt. Is this clear? Yeah.
Here we haven't assumed that vi is 0. It happens to be 0 because of the cross point.
Yeah, that's correct. So Vi in general is not 0. So because otherwise you will have no translational momentum either, or no angular momentum either, right? So so this is a general thing. Whether Vi is 0 or not, this term has to go to 0.
So how is the assumption for the point to be fixed at the inertial frame of reference?
If you don't have that, so then your d by dt of that point, whatever you're taking, that is not going to be giving you the cross product to be the momentum, right? So it's going to be an additional term that is there. That will not be the this velocity. This velocity is of the particle, remember. This velocity will be of this d by dt will be of the particle's velocity only if this is Ri. It is from an inertial point, inertially fixed point, right? So in other words, if you're taking from let's say an aircraft fixed point where an aircraft is also accelerating, then you will not get this term leading to the same velocity. It will be some velocity, and therefore they will not be parallel, and therefore it will not go to 0. Okay. So now coming to Cush's answers about the center of mass. Why is the same thing holding about the center of mass as well? You see that this orange equation is one and the same. I'm just replacing O's by C's when I go to this equation. So instead of the O subscript on left and right hand side, now I have the C subscript, that is the sum of the moments acting on the system of particles about the center of mass is equal to the rate of change of the angular momentum also calculated about the center of mass. Why is it so? It's a different reason, of course, but we use the same set of equations anyways. So we start with the second law for the angular momentum about the point O, which is summation MO is equal to dHO by dt, which we just now got. Now the angular momentums about C, that is the center of mass, and about O are related. We already showed that particular equation that if you know hc, you can get about h about any p. Now that p I will choose as an inertially fixed point, so therefore we'll call that as O. So all that I'm doing is that general equation, I'm replacing p by O, and then therefore RPC becomes ROC over here crossed with the translational momentum. So now this is what I have, right? So now you see that the applied moments about C, that is about the center of mass, and about O are related, because you take a moment about any point, you can take a moment about any other point. Those two are going to be related by the position vector between those 2 points that are concerned, which is of course ROC, right? So if you know the moments about the center of mass, you can find the moment about an inertially fixed point by taking the position vector from ROC to crossed with Fi to get that, right? So now thus if and only if, now you can very clearly see that this has to hold good in this case as well. Can you reason this out?
Whenever you go from the second to third step, are you like taking the cross product of both sides to get
From this to this?
Yeah. How do you
No. These are two independent things.
Oh, you're
Yeah. So this is talking about moments, the external moments, right? This is talking about angular moment of the system, right? Now we are trying to relate those two by using our generic equations. We're just substituting that there to get this, right? So the two choices that you can make for using this particular equation, what you saw in the previous slide, where C, instead of C you had O, inertially fixed point, and also if you have C, which is the center of mass of that particular system. So which is why this particular equation or extension of Euler's first law from translation to Euler's second law for rotation is so very useful and important.
Is it because the second term ROC plus F less to 0?
Come again?
So
Yeah.
This ROC cross FI, does that go to zero?
No,
Not necessarily.
not necessary. See, this is any inertially fixed reference point, and this is your center of mass, right?
Oh, I see. Yeah.
Yeah, and these are forces. Forces could be in any direction.
Yeah, you just combine the
Yeah.
energies together. Okay.
Yeah. Done. So now we want to get into the forms of the Euler's second law, which involve the angular momentum. So Euler's second law in terms of arbitrary points is much more complicated. So this is what I said. It's not for if you take any arbitrary point P, the external sum of external moments is not equal to dH by dHp by dt. Okay, why? Because you have this RPI cross MIAI, and your MIAI are nothing but the forces Fi, and therefore this cross product, yes, it is equal to the moment, but it is not equal to the angular momentum rate of change about that particular point P, arbitrary point P, except for two choices, P being O or being C. Okay. So Euler's second law is simpler, as we saw already, for particle set or rigid body in terms of angular momentum about two specific choices. One is the point which is fixed in an inertial frame of reference, which we called as O, for which of course summation of external moments is equal to the time rate of change in an inertial frame of the angular momentum about the same point O, inertially fixed. The other case is of course about the center of mass, even of course when the center of mass is moving. So in other words, you're not only having a pure rotation problem, but a problem of the rigid body involving both rotations and translations. Still of course we are talking of particle sets as well, so rigid body is a special case of that. So even if moving, if the center of mass is moving, or in other words translation is also involved in the motion, still your sum of external moments about the center of mass will be equal to the inertial time rate of change of the angular momentum about the center of mass. Okay, next we look at the conservation of angular momentum. You perhaps remember the conservation of translational momentum. Do you remember from high school physics under what conditions is translational momentum, or what you just probably call just momentum at that point of time, conservation of momentum? When is it valid? When is it valid, if at all it is valid? Under what conditions is momentum conserved? So you talk of conservation of mass, conservation of energy, conservation of momentum, etc. Right? They're not going to be always valid. There are certain conditions under which they are valid.
Oh, isn't it when the system is it's like energy is it's something about like the system.
It's just energy, right? There's no energy transfer out.
There's a subtle difference between them. See, energy conservation is different from momentum conservation. Energy conservation is what? When you do not have any dissipation. For example, no friction or no transfer of work or heat between the system and any external agency, right? So it's an isolated system essentially, right? So it's an isolated system in the sense that there's no energy transfer taking place between the environment and the system, right? So therefore energy is conserved, right? Now what should not transfer here for momentum to be conserved? Not necessary. You could still have.
Is it if there's is that through the external forces?
Precisely, yeah. So because what are we saying here? The law is that time rate of change of translational momentum is equal to external forces, sum of external forces. So if sum of external forces is equal to 0, therefore time rate of change of your translational momentum equal to 0, which means translational momentum is a constant, right? It's conserved. But now angular momentum is a little more complicated, so but holds the same kind of argument holds. So if applied moment is equal to 0 about a point, let's say that point is, we take special examples of that point, an inertially fixed point O, then of course your dh naught by dt equal to 0. So the same thing holds, right? Like our argument for translational case, conservation of translational momentum holds for angular momentum as long as the point chosen is a inertial frame of reference fixed point. Therefore, that you are taking moments about that to get to the angular momentum, right? Now, for a rigid body, what happens? It could be, for example, a pivot point. Okay, so that pivot point is fixed, like what example that you gave, the axis of rotation. So that it could be a pivot point which is fixed in both the inertial frame of reference as well as the rigid body, and not necessarily its center of mass, any point as long as it is fixed between the two, because once it is fixed in an inertial frame of reference, doesn't matter whether it is fixed or not with respect to the rigid body or not. Okay, so it could be a pivot point. For example, let's say the simple pendulum, it is hung from a particular location. That point is common for the inertial frame of reference as well as the pendulum, right? So that is a point that you can consider. So for that matter, any point which is fixed in an inertial frame of reference. Okay, so the example, of course, which you all gave in terms of rotation about a fixed axis which is not necessarily passing through the center of mass. For example, a flag, when your flag is attached at one edge rather than at its center of mass, right? So then you have this kind of a situation. The other, of course, is the case where the choice of the point is the center of mass, and therefore your dHc by dt equal to 0 if the applied moment equal to 0. Only for these two cases can you say that the angular momentum is conserved, because the angular momentum is not, as I said, not an instantaneous property of the system alone, but also a property which takes into account the point that you choose for taking the angular momentum. Therefore, the specific choice of the point becomes important, and angular momentum is conserved even in a situation where applied moment equal to 0, if and only if that point happens to be either O or C. Otherwise, angular momentum is not conserved in general, even when there are no external moments which are applied on the system of particles or the rigid body. Now, these two angular momentums, of course, are related, as we already saw. In fact, this equation we saw was holding for any arbitrary point to the center of mass, but we are specifically saying P is replaced by O, and therefore the angular momentum about O is angular momentum about the center of mass plus the cross product of the position vector from the point fixed in an inertial frame of reference to the center of mass with the translational momentum, right? So you would see that no moment. Of course, what does it mean? If there is no moment, what are the possibilities under which you do not have a moment on a system? External moments acting on a system can be 0 if
They either cancel out or there's none.
yeah, so you have positives and negatives and probably they all cancel out. Yeah, one case. Other situations in which you could have moments acting on a system equal to 0. Yeah, so if there are no forces, there will be no moments of forces, and therefore that will go to, so that's another example. So if there are forces and their moments are not that they're cancelling it out, but essentially what is happening in terms of where that force is acting, can you say then would the moment equal to 0? So the force itself equal to 0, as Atharva said. Now the moment is the cross product of a force and something, right? So that cross product can go to 0 even if F doesn't go to 0. When would it? Yeah, exactly. So which means that it means that that force is acting through the point about which you're taking the angular momentum. So essentially you're not having a momentum. Your momentum is 0, and therefore essentially you could have that kind of a situation as well. So one is, as you all said, as Atharva said, in fact, is that there is no force. That is one condition. The other is, of course, the force is passing through a point which is about which the moment itself is taken. Okay. So there could be other ways you can think about it, but these are two situations where you can very easily simplify a lot of problems, because very often you will encounter especially the second condition, and therefore you do not need to carry on very long involved derivations. You could drop off a lot of terms up front so that you carry on with the terms which you are sure are non-zero, right? So then conservation of angular momentum of course happens in an inertial frame of reference, because we already saw that holds not only for the choice of C but choice of O as well, where O is any point which is arbitrarily fixed in any arbitrarily fixed in any arbitrarily chosen inertial frame of reference, and therefore angular momentum conservation is not something so uncommon. Okay, so it is something which is going to be present even when you have forces, for example, as long as those forces are passing through that, because your moments will be zero, therefore your angular momentum is conserved, and therefore you can use that in a lot of problems.
So,
Yeah.
so for any arbitrary point, the angular momentum is not conserved
No.
because of the internal forces.
Exactly. Right. Yeah. So next we move on to another topic, kind of a very a simple extension of what we talked about, masses, which were important for translational motion. Now we have a concept of moment of inertia, mass moment of inertia in particular, but we generally say in dynamics just moment of inertia to refer to mass moment of inertia, and that is going to play the role of mass as far as rotational motion is concerned, and that's what we will see how it enters into the Euler's second law. So what are the forms involved there? So if you'd like to know a little more about it, you can read sections 4.3 and 4.5 into your book. So in other words, we have done pretty much with chapter 2 now. We are looking at chapter 4 already. Chapter 3 is already, 1 and 3 we had already covered in the previous classes. Now coming to the angular momentum expression for rigid bodies about their centers of mass. Okay, so this is the equation that we are going to eventually end up in this particular slide. So you have this particular equation, you see, involves two cross products. You have an RCQ in the upfront and at the rear. Would this be equal to 0 or not?
No.
No, right? So in fact you already saw an example, something similar to that, where you had same quantity appearing twice in a in a double cross product. You remember that? Yeah, this was the omegas which were involved, but they were on either side, and that turned out to be your centripetal acceleration, omega squared r. So it turned out to be along r. So this is what we want to look at, the angular momentum about the center of mass written in terms of this. So what is special about this Q? Let's look at. So particle set is hc. So your angular momentum about its center of mass for that particle set is nothing but the cross product of the position vector to those CIs and then mi vi. So you're going to sum up over all those n particles I equal to 1 to n. So now for a rigid body, what happens? Just you change the summation to an integral and you change the mi's into dm, right? The infinitesimal mass element dm that you have here, where of course this point q is a point in dm on rb. So that's what this means. So this point is q that we have in this final equation that we want to get here is not some arbitrary point, but it is the location of that infinitesimal mass element dm. Okay, and that's going to be of course different for different points in the rigid body. So you're going to be dealing with that, right? So now we can employ something which you guys used amply in the homework problems that you solved this morning, where you have the velocities of 2 points on a rigid body related to each other. Now those 2 points that now we choose are the location of that infinitesimal mass element dm, which is q, and the location of the center of mass c. Now we want to relate those two. We know, let's say the center of mass is velocity. We want to get that of any other particle, the velocity of any other particle on the same rigid body. All that we have to do is to add a term which is angular velocity of that rigid body in an inertial frame of reference, of course, crossed with the position vector from the center of mass to the arbitrary material point of mass dm. So thus we can say that your hc, now you can substitute for your VQ in this particular equation. From this third equation, you can substitute into your second equation over here for VQ, and when you do that, you will of course get two terms. But now, and the final result, I have only one term. So which term has gone to 0 and why? First of all, which term is retained? The second, right? So the first term has dropped out. Why? When can a cross product go to 0? Either this has to go to 0, that has to go to 0, or they have to be collinear, right? So are any of those conditions holding?
Well, I feel like it's collinear.
The collinear?
Is it?
See, Q is any point on the body, right? So you have a center of mass, let's say this is a cuboid. So you have it at the center of the length, center of the width, and center of the thickness. You have a point. But the position vector that you are interested in is going all around. So, and you're saying the cross product of every one of them is 0? Because this is just a fixed thing for the entire body. VC is fixed, right? Doesn't change. So VC is fixed. So why should that go to 0? This term remains, that goes to 0.
Is VC going to 0?
No. So in general, the body is not only rotating but also translating. Yeah. So in the special case where there's only rotational motion, you're right that that would go to 0. But this is always true. This is always true. If this is true, this is always true. So
Is it because you have RCQ cross RCQ?
no, that is what is retained. That is not going to 0.
Oh,
That's there. The other one is this is similar to what you guys were doing, right? Omega cross r cross omega, where it was giving you a centripetal acceleration. So that remains, right? So you ended up with a minus omega squared r term, which was always there. So this will not go to 0 in general. Okay? That will go to 0, the first term. Why? Let me give you a hint that the cross product may not go to 0, but still the first term will drop out. Why?
wait, so both thing, the first one goes to 0, but both thing A or A not. Oh, is it because it's DM? Because the Q is a differential point. It's
Yeah.
it's a point on the differential.
Yeah.
If you take it over the entire mass,
Uh-huh.
you're basically taking every single point
Yeah.
on the entire
Yeah.
mass.
Yeah.
And all those R's basically, because they're all in different directions,
Mhm.
they cancel each other out.
R's don't cancel each other out, but RDM will cancel each other. Why? Because the point that we are taking the position with respect to is C,
It's the center.
and that's your definition of your center of mass.
Which is
Because your VC is a constant, it's not dependent on your DM, it will go out of the integral. If you take the first term, I can take the cross VC out of the integral, and I will just have to integrate RCQ DM. And integral of RCQ DM is 0 by definition of the center of mass, right? So that's why the first term drops out and you're left with just this particular term, okay? Yeah. Let me see, maybe I'll just cover this particular slide. So the angular momentum expression for 2D rigid bodies about the center of mass. So we're just specializing. Whatever we've done so far is generally valid for 3D and therefore also for 2D. So it's going to be obviously much simpler when you specialize it to 2D motion, which means that there's only one angular velocity. In other words, the angular velocity vector remains constant throughout, so it's in the same direction, right? Now for 2D rigid bodies, you have RCQ, that is the term that we were left with in the previous slide, the position vector from the center of mass to the individual infinitesimal mass element Q. That is equal to, of course, because it's a 2D problem, there are only I hat and J hat terms, no K hat term, and that's going to be XC I hat plus yc j hat, right? So now your omega is equal to omega z k hat, because your direction of the angular velocity remains fixed. It's not instantaneous, it is fixed throughout the duration of interest, right? So that's for your 2D rigid bodies. You would have your angular momentum about the center of mass. Now you can replace that RCQ that you had in the previous expressions on the previous slides. Now you can replace that with an xc squared plus yc squared, which is the magnitude of your RCQ times dm, and then of course your omega z k hat instead of the angular velocity, because that was a,
So that's what you get if
yeah,
you
yeah,
expand it.
yeah,
Oh.
precisely. So where of course you can now introduce this concept of the moment of inertia about the z-axis, about a point C that you have, which is your center of mass, and this is your what you're defining as, because it's about the z-axis, is the sum of the squares of the other two coordinates, xc squared plus yc squared multiplied by dm, and this is called as the rigid body's moment of inertia about the z-axis, which is passing through the center of mass. Okay, so which is what this notation means. So the subscript means about which axis, and the point, the superscript means about which particular point. And if you change either one of them, you're going to, in general, have different results for different rigid bodies, for the same rigid body also. Right? So is this clear? So maybe we will stop here and continue in the next class. If there are any questions, I'd be happy to answer.
Would you say
So it's essentially this. So your integration over here, whatever is within your brackets.
yeah, you just do.
Yeah. So you just leave your omega c z k hat separately and take that. So now you have your very similar to how you're having your translational momentum or momenta as mass times the velocity. Here you have a moment of inertia times the angular velocity. So this is possible to express in such a simple way for 2D motion, where the angular velocity is along a fixed axis, and you are introducing your coordinate system xyz in such a way that z is along the axis of rotation, and therefore k hat is the unit vector along that, and therefore your angular velocity becomes omega z k hat, and which is why you got this equation first of all. Now you're just replacing that first term in terms of the moment of inertia IZZC, and therefore you have a much simpler form that you have here for 2D motion as opposed to the general expression you had for the 3D motion. So, any other questions?
Can you like kind of explain it there? Whenever you said this is kind of like a couple stuff. When you said Q is a point in the DM of the body, you wrote that like Q. Whenever you're doing like RCQ cross BC, so Q is a point on the DM of the body. Can you kind of explain?
Yeah, sure. So you have an inertial frame of reference I, right? So let's say you have I hat, j hat, k, right? And then you have some arbitrarily shaped rigid body. We call that as B. Okay. So now, if I want to calculate the properties of this particular rigid body, I'm just taking an infinitesimal element over here at some location, which is over here. I will call the center of that infinitesimal mass dm as q, and this is your O, right? Now, I can also reach to that by first going to the body's center of mass, C, and then going over there, right? So this is nothing but your ROC, so OQ, ROC and RCQ, right? Now if I want to get the mass, for example, I just integrate dm, which is equal to integral rho dv, right? Now if I want to get any quantity like what you are having, like r's or whatever, you have to take that r and then integrate. So for example, if you want to get the center of mass, you are going to integrate your r OQ you're going to get the center of mass. So you see the association of Q with D. So what specifically would you like to know now?
So how is it that RCQ cross VQ is 0 whenever you do the integral of dm?
RCQ cross VC, we had, right?
VC,
Yeah. You're talking of this term, right?
Yeah.
Yeah. So let me rewrite that first term over here. It is an integral of RCQ cross VC dm, right? Now this VC is a constant, it's a velocity of the center of mass, right? So I can write this as integral of RCQ dm cross with VC. Now this, by the definition of the center of mass, has to go to 0. That's the reason why it is.
Oh, that makes sense.
Yeah.
The whole thing
You can even use this, say the location, and then you use this, that ROQ is equal to ROC plus RCQ, and these 2 points are not changing with each other. So once again you can use that also to prove the same thing. But essentially you will see that this is a direct fallout of your center of mass definition, that this is equal to 0. So irrespective of what VC is, doesn't matter, and the directions also don't matter, this term itself is going to 0 after integration. Okay, thank you.